Okay, hello everyone. We are back to really revise and summarize Chapter 2, Kinetic Particle Theory, as well as the portion on the elements, compounds, mixtures in Chapter 4 of our chemistry textbook. All right, so this is in preparation, of course, for your Sec 3 end of year exam. Now, we start with Kinetic Particle Theory, which doesn't have a lot of content. It is really just two main concepts. The first concept has to do with the arrangement and movement of particles in the three states of matter: solid, liquid, and gas. Okay, so now we go to the arrangement of particles. You must be able to describe arrangement. So what is under arrangement? So for example, particles in a solid are closely packed. They are closely packed in a regular manner. Another way to say regular, orderly. So when we ask for arrangement, what we are looking for really is the spacing or packing, as well as whether it's regular or irregular. So for a liquid, the particles are also closely packed, but the difference is it's in an irregular arrangement. Okay, another way to say that is disorderly arrangement. And finally, for particles in a gas, if you look at the drawing of the particles in a gas, you can tell that they are spaced far apart in a irregular manner. Okay, so this is how you describe the arrangement of particles in the three states of matter. Deal with the packing, as well as deal with whether it's regular or not. Okay, so now that we have dealt with the arrangement of particles, which has to do with packing or spacing, as well as how regular the arrangement is, now let's move on to movement of particles. In a solid, the particles vibrate about fixed positions. What this means is that particles in a solid cannot move freely. They can only be in fixed positions and vibrate about those fixed positions. Okay, so their only movement is actually around their fixed positions. Now, for a liquid, the particles can now move freely because the particles are able to slide past or slide over one another easily. So this tells you that in a liquid state, the particles can actually move freely, and this has important consequences. For instance, because the particles can move freely, a liquid can be poured, a liquid can flow freely. And finally, for a gas, the particles, they move in all directions at high speeds. Okay, so really you are considering that the particles in a gas, they are moving and whizzing around in all directions at very high speed. So this is how we describe the movement of particles. We go from solid, which is just vibrating about fixed positions, liquid sliding over one another easily, and finally for a gas, really moving in all directions at high speeds. And with that, we can come to the conclusion, just by looking at the movement of the particles, we can conclude that the energy, in terms of energy of solids, liquids, and gases, we can come to this conclusion. The lowest in energy will be a solid. Then a liquid is higher than a solid in energy, because in a liquid, the particles can actually slide over one another. And finally, a gas should be the highest energy, because in a gas, the particles move in all directions at high speeds. This tells you that the energy of particles in a gas should be the highest. Okay, so in terms of the arrangement of the energy, gases should have the highest energy when compared with solids and liquids. And so now, moving on, now that we have seen the arrangement and movement of particles in solids, liquids, and gases, we know how to describe the arrangement and movement. Now let's look a bit deeper at the concept of energy. So as mentioned, In terms of energy, the gases have the highest energy. What this means is that as we go from solid to liquid, the energy goes up. As we go from liquid to gas, the energy also goes up. Okay? This is a logical consequence of the speed of the particles inside solids, liquids, and gases. So now let's try to fill in the names of these processes. So for example, from solid to liquid, this is called melting. From liquid to gas, this is called boiling or evaporation. Okay, they are not exactly the same. Okay, but for us, we don't have to go into the differences between boiling and evaporation right now. All right. So from liquid to gas is boiling or evaporation. And then we realize that as we go from gas back down to liquid, the energy actually goes down. Now, gas to liquid is called condensation. So the process is called condensation. Finally, liquid to solid, freezing. So I've deliberately color-coded the arrows as red as well as blue. And there's a reason for this. You realize for melting and boiling evaporation, the energy goes up. Now, this energy comes from the surroundings. For the energy to go up means they must have absorbed energy. So these processes take in energy. So melting, boiling, evaporation involves taking in or absorbing energy from the surrounding. Whereas condensation and freezing is the reverse. Because the energy level goes down, that means energy is actually released. They release or give out energy to the surroundings. Okay, so you do not need to know which processes take in energy and which processes give out or release energy. So these are the two different sets of processes. Remember, if you are going up solid, liquid to gas, you take in energy. If you are coming down gas to liquid to solid, you release or give out energy. Okay? So now let's move on to representing these energy changes on a graph. And this graph that represents some of these changes is called the heating curve and the cooling curve. Today, we will look at the heating curve. Now, heating curve basically tracks temperature in degrees Celsius with time. Time can be minutes, can be in seconds. So basically, the heating curve tracks the temperature changes in a sample as it's being heated up. So as it's being heated up, your temperature change looks something like that. Okay, so this is a typical heating curve for a solid. So what happens is that you start off as a solid. So the substance is originally a solid and is being heated up. Now, it will reach a certain point where the temperature remains constant. When it remains constant, this means that it's changing state. That means it is changing from the solid to the liquid state. And of course, this is called melting. Solid changing to liquid is called melting. And hence, I can work out the temperature at which it melts. If I trace it back to the y-axis, I can find the temperature at which melting happens. And that's called the melting point. The melting point of a substance, just trace it back to the y-axis. You take the first horizontal region, the first flat region, trace it back to the y-axis. Now, during melting, you do not have only liquid because it's in the process of melting. At melting, you will have both solid and liquid. And this is an important concept. So during melting, you have both states present. Now, after melting finishes, when melting ends, Of course, it is entirely liquid. And again, the liquid is heated up and the temperature continues to increase until it reaches the next flat region. And the next flat region, again, is flat. The temperature doesn't change. It is a flat region because it's changing state. Liquid changes state to gas. This is boiling. So again, how do you find the temperature? You just trace it back to the y-axis. So that gives you the boiling point of the substance. The boiling point is the temperature at which boiling happens. And when you have boiling, you have both liquid and gas present. So remember, when it's changing state, both states must be present. And finally, after boiling ends, you have entirely gas. So this is a typical heating curve. You can be asked to list down which states are present. Is it solid? Is it solid and liquid? Liquid and gas, or gas? The next type of question could ask you, what is the melting point? What is the boiling point of the substance? Okay, so these are all possibilities. And finally, we need to know why temperature remains constant. You notice that the graph is flat. If the graph is flat, that means the temperature remains constant. And it remains constant during melting, boiling. These are change of state. It is changing from the solid to the liquid state, from the liquid to the gaseous state. So during change of state, the temperature remains constant. But why? The key is the energy. The energy taken in or absorbed is used to overcome the forces of attraction between particles. So it takes in heat energy, but all that energy is actually used to overcome the attractive forces or the forces of attraction between particles. As a result of that, there is no change or no increase in the kinetic energy of the particles. So the energy only goes into overcoming forces of attraction. It does not increase the kinetic energy of the particles. Now, why is kinetic energy so crucial? It's crucial because temperature is a measure of the kinetic energy. Temperature is actually a measure of the average kinetic energy inside particles. So if there's no increase in kinetic energy, it's the same as saying temperature remains the same. Because temperature is basically kinetic energy of the particles. So this explanation fully explains to you why the graph shape is flat whenever there's melting and boiling. This is because during the change of state, all the energy taken in is actually only used to overcome the forces of attraction between particles. There is no increase in the kinetic energy of the particles as a result. Okay? Okay, so now let's move on to elements, compounds, and mixture. Okay? Now, so we have finished kinetic particle theory. Let's move on to elements, compounds, and mixture. Now, the whole study of elements, compounds, and mixture, what are they? Now, the whole idea is we have many chemicals around us. Chemicals can also be called substances. Water is a substance. Carbon dioxide is a substance. Oxygen that you breathe in is a substance. The air around you is also a substance. There are so many chemical substances. So we need to know how to classify them. And so, to classify chemical substances, we look at the types of particles they contain. So based on the particles, we can classify them as elements, compounds, or mixtures. So now we will look at every single one of these categories in turn, and we will draw some interesting diagrams. Now, elements should be quite easy to identify, because if you look at the particles, they look something like that, or something like that. Right? How do you know from these diagrams that these are elements? From these diagrams, you can tell that they are elements because they contain only one type of atom. So every single circle there represents an atom. So they contain only one type of atom, hence they are elements. Okay? Now, not only that, now that you have done kinetic particle theory, we can say that this is a gaseous element. Because we can see that the particles are spaced far apart in a disorderly arrangement, whereas the one on the right is a solid element because the particles are closely packed in a regular, orderly arrangement. Okay, so the idea is elements must only contain one type of atom. Okay, now if you look at the two drawings that I've drawn, they are both elements because they contain only one type of atom. Now, the one on the left is a gas, the one on the right is a solid. Now, besides that, the one on the left is also diatomic. Diatomic means it's made up of two atoms in a molecule, like O2 or N2 or H2. These are your diatomic elements: oxygen, nitrogen, and hydrogen. Okay, these are common diatomic elements. They are not the only ones. You will encounter more as time goes by, but these are the common ones. Okay, and that's really it for elements. And finally, you should know elements are arranged in order of proton number. Okay, in the periodic table. So you can find elements in the periodic table. So if you can find it in the periodic table, it's an element. So for instance, oxygen is an element, nitrogen, element, iron, element, because they are all in the periodic table. However, if you cannot find it in the periodic table, it's not an element. For example, water. Water is not in the periodic table, right? Therefore, water is not an element. Steel. Steel is not an element because steel is not in the periodic table. Okay? Now, in the periodic table, of course, you have two types of elements. There's metals and non-metals. I hope we know by now, the metals are located on the left-hand side of the periodic table. The non-metals are located on the right-hand side of the periodic table. Okay, that's how we divide the metals from the non-metals. Okay, next we move on to compounds. Now, compounds look something like that. So this is a typical compound. So this is a compound. Why? Because you can see now there's more than one type of atom. This tells you it contains two or more elements. And the elements, you can see they are joined together in the diagram. When we join the different elements together, we are saying that it's chemically combined. So by joining them physically, all right, in the diagram, it means that there's some chemical bond between them. Now, they are not just chemically combined in some random manner. You can clearly see there's two dark circles for each white circle. 2 dark to 1 white. So we can say that it's chemically combined in a fixed ratio. And what is this fixed ratio? In this case, you can see from the diagram, 2 dark circles to 1 white circle. So this could be, for example, water. You have 2 hydrogens bonded to 1 oxygen. 2H is to 1O. Therefore, that is a fixed ratio, right? So compounds contain 2 or more elements chemically combined together in a fixed ratio. And because it's combined together chemically, we know that it's formed by a chemical reaction. So for example, to form water, you may have to take hydrogen and burn it in oxygen. Burning is a chemical reaction. And because it's formed by a chemical reaction, usually compounds, when they are formed, they release heat and light energy when formed. So for instance, if you burn hydrogen in oxygen to form water, it releases a lot of heat. Okay? This tells you that it's a chemical reaction and therefore it's chemically combined. And because it's chemically combined, it cannot be separated. Separated by physical methods. So what are physical methods? Physical methods are things like filtration, chromatography, distillation, and so on. So I cannot break water down into H and O just by filtration. I can't do that. All right? And this is a result of it being chemically combined together. Okay? So these are the characteristics of a compound. So these are the things that you should know, the properties of a compound. All right? Okay, and finally we go to mixtures. And now for mixtures, you see that, hey, there's actually a variety of things that we can do. So you notice now this is a mixture. This is also a mixture. Okay, so both are mixtures. So what can you say from the diagrams about these things? Mixtures, they also contain 2 or more, but they contain 2 or more substances. They need not be elements, they are just substances in general. They are physically mixed together. They are not chemically combined, they are just physically mixed. They are not chemically combined. And it's not chemically combined in a fixed ratio. Meaning, mixtures do not have fixed ratio, proportion, or composition. So you must get used to these terms. They don't have a fixed ratio, proportion, or composition. So ratio, proportion, and composition, they mean the same thing. Okay, so these are mixtures. They contain 2 or more substances, okay, which are physically mixed together only. They are not chemically combined. They don't have a fixed ratio. And because they are not chemically combined, they can be easily separated. Because they are not joined together. So we can easily separate them by physical methods. And what are the physical methods? Just now we said filtration, distillation, evaporation, crystallization, and so on. All right. So your physical methods basically is what you learn in chapter 1, separation techniques. So if you have missed out on chapter 1, please go back and watch the video for chapter 1, separation. Those are all the physical methods of separating mixtures. Okay. Now, so that's really what I need to know about mixtures. But I've deliberately drawn two different arrangements of mixtures because now you may be asked to go deeper and explain, it's a mixture of what and what. So for example, if I zoom in at this, the one on the left, you can see there's one element, the white circles. There's another element, the black circles. So mixtures can be mixtures of two elements or more elements. These elements are just mixed together. They are not chemically combined. You can tell that they're not chemically combined because they're not joined together. The white doesn't join with the dark circle, right? Therefore, it's two separate elements just mixed together. And then on the right-hand side, what you have is an element and a compound. And therefore, mixtures can also be a mixture of an element and a compound. So mixtures, there's a diversity here. You can mix elements together. You could mix elements and compounds together. You could also mix compounds and compounds together. But the idea is it's just a physical mixing. There's no fixed ratio, no chemically combined. And because of that, we separate them simply using physical methods like filtration, distillation, evaporation, crystallization, chromatography. Okay? So all the separation techniques, in case you forgot, this is chapter 1. So go back and watch the video for separation techniques, where we will cover all the separation techniques such as filtration, evaporation to dryness in detail. Okay, and that really brings us almost to the end of elements compounds mixture. The very last part, I'm just going to zoom out so that we look at the elements compounds mixture as a whole. Okay, so now let's zoom out and look at the whole chart of elements, compounds, and mixtures. So we started off by saying, okay, chemical substances can be classified as element, compound, or mixture, all right, depending on what types of particles they contain. Now, if you look at elements and compounds, you realize that, hey, elements and compounds have something in common. Elements and compounds, they contain only one kind of molecule, right? H2O consists of only H2O. Elements like oxygen contain only oxygen, O2. So, because they contain only one type of molecule, we say that they are pure. So, elements and compounds are pure. And if they are pure, how do you test and verify and confirm that they are pure? To verify that something is pure, we measure the melting point. If it's pure, it has a fixed melting and boiling point. For instance, H2O, water melts at 0 degrees Celsius. That means it will only melt at 0 degrees Celsius. It's not going to melt from -2 to like 4 degrees Celsius. It's not. There is no range of temperatures. It must be 0 degrees if water is melting, if the water is pure. All right. Now, on the other hand, you notice that mixtures are the opposite. Mixtures contain more than one substance and they are just mixed together. So mixtures are impure by definition. So how can I tell that they are impure? They are impure because they do not have fixed melting and boiling points. That means that they might melt from 0 degrees all the way to like 3 degrees. So it's a range of temperatures. So how can you tell it's not fixed when you are told that the melting point is like 0 all the way to like 3 degrees Celsius? That is a telltale sign, an indicator to you that, hey, the melting point is not fixed. Okay? So purity, whether something is pure or not, is verified, is confirmed by testing and measuring the melting and boiling points. Okay, that's the only way to tell whether something is pure or not. Okay, so that really brings us to the end of elements, compounds, and mixture. Once you have understood this idea of pure, pure means elements or compound. Okay, both elements and compounds can be pure. So pure means fixed melting point. Impure must be mixture. It doesn't have a fixed melting and boiling point. Okay, and that really concludes this segment on elements, compounds, and mixtures. Okay, so thank you for attending today. Ensure you have taken everything down, and if need be, go back to the video and revise and rewatch again. Thank you.